I wish to welcome you all for this video tutorial session. Now we are going to see about combinational circuits. Before going to combinational circuit, first let us see what is combinational circuit, what are combinational circuit, where the combinational circuits are used. The first question is, what is combinational circuit? The combinational circuit is a logic circuit in which the output at any time depends only on the present combination of inputs. In other words, we can define when the logic gates are connected together to produce a specific output for certain combination of inputs, then the resulting circuit is called combinational circuit. The second question is, what are combinational circuits? The combinational circuits are adder, subtractor, multiplexer, demultiplexer, parity generator checker, and code converter, etc. The third question is, where the combinational circuits are used. The combinational circuits are used in arithmetic logic unit of central processing unit to perform the operation like addition, subtraction, multiplication and division. Now let us see the basic block diagram of combinational circuit. This is the basic block diagram of combinational circuit. It consists of n inputs, number of logic gates and m outputs. This combinational circuit accepts the signals from n inputs and generates m outputs based on the logical combination of gates. Now we are going to see about how the combinational circuits can be designed. Actually, the design of combinational circuit starts from the specification of the design objective and ends in a logic diagram or a set of Boolean functions from which the logic diagram can be obtained. Actually, there are 6 different steps to be followed to design a combinational circuit. The first step is define a problem statement. The second step is determine the required number of inputs and outputs. Then the third step is assign a letter symbol to each input and outputs. The next step is derive a truth table that defines the relationship between input and outputs. The next step is obtain a simplified Boolean expression for each output as a function of inputs. Then the last step is draw a logic diagram for each output by using basic gates. First let us consider the simple problem. Design a combinational circuit consists of 3 inputs and 1 output that will produce logic 1 output when the input is less than 3, otherwise the output will be logic 0. Let us take f is called the output variable, x, y, z are the input variables, which is equal to logic 1 when the input is less than 3. Otherwise the output will be 0. This is the problem statement. From this problem statement, determine the required number of inputs and outputs. Let us take x, y, z are the input variables and f is called the output variable. Next let us see the truth table for this combinational circuit. X, y, z are the input variables, f is called the output variable. Here we have 3 input variables. So for 3 inputs there are 8 possible combinations. The combination starts with 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. There are 8 possible combinations. The combination starts with 0 0 0, ends with 1 1 1. Actually, from the specification we know that the output will be logic 1 when the input is less than 3. For the first 3 combinations, the output will be 1. For the rest of the combinations, the output will be 0. This is the truth table for the given problem. Next, from this truth table, let us derive the Boolean expression by using K-map. Here we have 3 input variables, so we need 3 variable K-map to find the Boolean expression. X, Y, Z are the input variables. Which consist of 8 squares to represent the min term. Actually, for the first 3 input combinations, the output will be 1. This first square represents 0, 0, 0. Then the output will be 1. Then the second square represents 0, 0, 1. 1. Then third square represents 0, 1, 1. Then the output will be 0. Then the fourth square represents 0, 1, 0. The corresponding output is 1. For the rest of the combinations, the output will be 0. Then from this K-map, we have to find the Boolean expression. In this K-map, we have 2 possible groups. These 2 ones forms group 1. Then this one is adjacent with leftmost one. Then this one forms another group called group 2. Here the first group represents X bar, Y bar, which eliminates the variable called Z. Then the second group represents X bar, Z bar, which eliminates the variable called Y. This is the required Boolean expression. F is equal to X bar, Y bar plus X bar, Z bar. Then by using this Boolean expression, we have to draw the logic diagram. We have 3 input variables X, Y, Z. To implement this combination circuit, we need 2 2-input AND gate, 1 2-input OR gate and 2 inverters. In the first term, X bar is ANDed with Y to get X bar, Y bar. Then X bar is ANDed with Y to get X bar, Z bar. Finally, these 2 terms are ORed to get the final expression F. This is the required logic diagram for the given combinational circuit, which consists of 3 inputs. Here these 3 inverters are used to take the complement of the inputs. Then for this AND gate, the inputs are X bar, Y bar. Then the output will be X bar into Y bar. Then for these AND gates, the inputs are X bar and Z bar. Then the output will be X bar into Z bar. Then these 2 are ORed to get the final expression F, which is equal to X bar, Y bar plus X bar, Z bar. This is the logic diagram for the given combination circuit. Next, let us see adders. Now we are going to see about adders. What is meant by adder? Adder is a combinational circuit that performs the arithmetic sum of 2 binary numbers. The adder classified into 2 types. The first one is half adder and the second one is full adder. What does mean by half adder? Half adder is a logic circuit that performs the addition of two binary digits. First we will see half adder. First let us start with basic block diagram of half adder. This half adder consists of two inputs x and y and two outputs s and c. S represents sum, c represents carry. This is the basic block diagram of half adder. Next let us see the rules for binary addition. Zero plus 0 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 1, 0. Here the first three addition produces sum of one digit, the last binary addition produces sum of two digit. Here the higher significant bit of this result is called carry, then LSB bit is called sum. So carry is equal to 1, sum is equal to 0 for the last addition. These are the basic rules for binary addition. Now let us see the truth table for half adder. Here we have two inputs and two outputs. Let us take x and y are the inputs and s and c are the outputs. Here the two inputs denoted by x and y represents the two significant bits to be added, and the output variables denoted by s and c, s for sum and c for carry. Here we have two input variables, so there are four possible combinations: 0 0, 0 1, 1 0, 1 1. Here the first combination is 0 0, then 0 plus 0 is equal to 0. The sum will be 0, there is no carry, then the carry will be 0. The second combination is 0 1, 0 plus 1 is equal to 1, then there is no carry, then the carry will be 0. Then third combination is 1 0, then 1 plus 0 is equal to 1, then the carry will be 0. And the next combination is 1 1, then 1 plus 1 is equal to 1 0, here the sum will be 0, the carry will be 1. This is the truth table for half adder. The sum will be high for the combination 0 1 and 1 0, then the carry will be 1 when both the inputs are 1. Then from this truth table let us derive the Boolean expression for sum and carry. First one for sum. Here we have two inputs, so we need two variable K map. X, y are the inputs, x may be 0 or 1, y may be 0 or 1. Here it consists of 4 squares, each square representing one minterm. Here the sum will be high when the inputs are 0 1 and 1 0. In this K map we have two isolated ones. Then the sum expression will be this one represents x bar y, then this one represents x y bar. This is the sum expression. Here the sum is expressed in terms of sum of product form, then this can be written as x xr y. This is the Boolean expression for x xr y, x bar y bar plus x y bar, which is equal to x xr y. Now this can be written as x xr y. Then let us see the Boolean expression for carry. Here the carry will be 1 when both the inputs are 1. So the carry expression will be C is equal to x into y. Then from this expression we have to draw a logic diagram for half order. Here we have two input variables x and y and two outputs sum and carry. The sum expression will be s is equal to x XOR y. Then the carry expression will be c is equal to x into y. Now the sum will be s is equal to x XOR y, then carry is equal to x into y. This is the logic diagram for half order. Next, let us see the full adder. Before going to full adder, first let us see the limitations of half order. Half order has two inputs and there is no provision to add carry generated from the last stage. So in order to avoid the limitations of half order, full adder is designed to perform addition of 3 binary digits. What is meant by full adder? Full adder is a combination circuit that performs the arithmetic sum of 3 binary digits. Now let us see the basic block diagram for full adder. This is the basic block diagram for full adder. It consists of 3 inputs and 2 outputs. S represents sum, C represents carry. The 2 of the input variables represent the 2 significant bits to be added, and third input Z represent the carry generated from the previous stage, and the output variable are denoted by S for sum, C for carry. Next, let us see the truth table for full adder. Here we have 3 input variables, so there are 8 possible combinations: 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. Here the input combination starts with 0 0 0 and ends with 1 1 1. Here the outputs are S and C. The first combination is 0 0 0, then 0 plus 0 plus 0 is equal to 0. Then the sum will be 0, then there is no carry, then the carry will be 0. The second combination is 0 0 1, 0 plus 0 0, then 0 plus 1 1. Sum will be 1, then the carry will be 0. Similarly, we can write 1 0. The next combination is 0 1 1, 0 plus 1 1, 1 plus 1 1 0. Then the carry will be 1, the sum will be 0. The next combination is 1 0 0, then the sum will be 1, carry will be 0. The next combination is 1 0 1, then the carry will be 1, sum will be 0. Then the next combination is 1 1 0, then the sum will be 0, carry will be 1. Then the next combination is 1 1 1, then the sum will be 1, carry will be 1. From this truth table, let us derive the Boolean expression for sum and carry. Here we have 3 input variables x, y, z. So we need 3 variable came up to find the Boolean expression for sum. Here the sum will be 1, for the combination 0 0 1 0 1 0 1 0 0 1 1 1 1 1. Here the sum will be 1 for the combination 0 0 1 0 1 0 1 0 0 1 1 1. Then from this K map we can find the Boolean expression for sum. Then the sum expression will be, this one represents x bar y bar z, plus this one represents x bar y z bar. Then this one represents x bar z bar. Then this one represents x y z. Then here the sum expression is expressed in terms of sum of product. Now this expression can be simplified by using x exclusive OR gate. While taking first two term x bar is common, then it can be simplified as x bar into y bar z plus y z bar. Then similarly we can write x into y bar z bar plus y z. Now this can be written as, we know that y bar z bar plus y z bar is equal to y xr z plus x into, this can be written as y x nor z. Now this can be written as x bar into y xr z plus x into y xr z whole bar. Now this y x nor z whole bar can be written as y xr z whole bar, then which is equal to x bar, let w is equal to y xr z, this can be written as x bar into w plus x into w bar. Now this looks like xr expression. Now this can be written as x xr w. We know that w is equal to y xr z, then which is equal to x xr y xr z. Then the sum expression can be reduced as s is equal to x xr y xr z. Next let us see the K-map simplification for carry. We need 3 variable K-map to find the Boolean expression for carry. X, Y, Z are the inputs. Here the carry will be 1 when the inputs are 1 1 0 1 0 1 1 1 0 1 1 1. Then in this K-map we have 3 possible combinations. These 2 adjacent ones forms group 1, these 2 adjacent ones form group 2, these 2 adjacent ones form group 3. Then the carry expression will be, this one represents x z plus this one represents y z, then this one represents x y. This is the Boolean expression for carry, x z plus y z plus x y. Then using these 2 Boolean expression we can draw the logic diagram for full adder. Now we can draw the logic diagram for full adder. Actually we have 3 inputs x, y, z. Then the sum expression will be x xr y, y xr z. So we need 3 input XOR gate to get sum. Sum is equal to x xr y xr z. Then the carry expression is x z plus y z plus x y. the input x and z are get ANDed to get xz. Then the next term is yz. Y and z are ANDed to get yz. Then x and y are ANDed to get xy. Then these three are ORed to get the carry expression. The carry expression is xy plus yz plus xz. This is the expression for carry. The next topic is subtractor. What is meant by subtractor? Subtractor is a combinational circuit that performs the subtraction of two binary numbers. The subtractor classified into two types. The first one is half subtractor, the second one is full subtractor. What is meant by half subtractor? Half subtractor is a combinational circuit that performs the subtraction of two binary digits. Now let us see the basic block diagram for half subtractor. This is the basic block diagram for half subtractor. It consists of two inputs x and y and two outputs borrow and difference. Borrow denoted by B and difference denoted by D. Now let us see the basic rules for binary subtraction. Zero minus 0 is equal to 0. Then 0 minus 1 is equal to, actually here the 0 is less than 1, then we cannot subtract 1 from 0. So we need to get a borrow. So this can be replaced by 1 0 minus 1. Now the difference will be 1 with a borrow 1. The next combination is 1 minus 0. 1 minus 0 is equal to 1. The next one is 1 minus 1. 1 minus 1 is equal to 0. Next let us see the truth table for half subtractor. Here we have two inputs, so there are four possible combinations: 0 0 0 1 1 0 1 1. The first combination is 0 0 0 minus 0. The difference will be 0. There is no borrow, then the borrow will be 0. The next combination is 0 1 0 minus 1 is equal to 1. Then there will be a borrow will be 1. The next combination is 1 0. Then the difference will be 1. Borrow will be 0. The next combination is 1 1 1 minus 1 0. Then the difference will be 0. Borrow will be 0. Then from this truth table let us derive the Boolean expression for borrow and difference. First one for difference. Here we have two inputs, so we need two variable came up. Here the difference will be 1 for the combinations 0 1 and 1 0. So the difference expression will be x bar y bar plus x y bar. Then this can be written as x XOR y. This is the Boolean expression for difference. Next, let us see the Boolean expression for borrow. We have two inputs x, y. So we need two variable k map. Here the borrow will be 1 for the combination 0 1. So the borrow expression will be b is equal to, this one represents x bar y. Then from this Boolean expression we have to draw the logic diagram for half subtractor. Next one, the logic diagram for half subtractor. Here we have two inputs x, y. We have two outputs difference and borrow. The difference expression will be x XOR y. Here x XOR with y to get the difference. So it's equal to x XOR y. Then the borrow expression will be x bar into y. Here x is inverted to get x bar, then x bar is ANDed with y to get borrow, which is equal to x bar into y. This is the logic diagram for half subtractor. Next we are going to see about full subtractor. Next let us see the truth table for full subtractor. Here we have three inputs x, y, z, two output difference and borrow. Here we have three input variables, so there are 8 possible combinations 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. The first combination is 0 0 0 0 minus 0 0 0 minus 0 0. The difference will be 0, then the borrow will be 0. The second combination is 0 0 1 0 minus 0 0 0 minus 1, the difference will be 1, the borrow will be 1. The third combination is 0 1 0 0 minus 1, the difference will be 1, the borrow will be 1. The third combination is 0 1 1, then the difference will be 0, then the borrow will be 1. Then the next combination is 1 0 0, then the difference will be 1, the borrow will be 0. The next combination is 1 0 1 1 minus 0 1 1 minus 1 0 0. Then the next combination is 1 1 0 1 minus 1 0 0 minus 0 0. Then there is no borrow, then the borrow will be 0. The next combination is 1 1 1 1 minus 1 0, then the 0 minus 1, the difference will be 1, then the borrow will be 1. Then from this truth table let us derive the Boolean expression for difference and borrow. First one for difference. Here we have 3 input variables, so we need 3 variable k map which consists of 8 squares. X, y, z are the input variables. Here the difference will be 1 for the combination 0 0 1 0 1 0 1 0 0 1 1 1. Here we have 4 isolated ones. So the difference expression will be x bar y bar z plus x bar y z bar plus x y bar z bar plus x y z. Here the difference expression is expressed in terms of sum of product form. Then this can be simplified by using XOR operation. While taking the first 2 term, x bar is common, so it simplified as x bar into y bar z bar plus y z bar plus similarly x into y bar z bar plus y z. then this can be written as x bar into y xr z plus x into y xr z whole bar. Let take w is equal to y xr z, then this can be written as x bar into w plus x into w bar, which is equal to x xr w. We know that w is equal to y xr z, then which is equal to x xr y xr z. This is the Boolean expression for difference. Then let us derive the Boolean expression for borrow. Here the borrow will be 1 for the combination 0 0 1 0 1 0 1 1 1. In this K map we have 3 possible groups. Then the first group represents x bar z. Then the second group represents x bar y. Then third group represents y z. Now we have the Boolean expression for difference and borrow. By using these two expressions we have to draw the logic diagram for full subtractor. Now let us see the logic diagram for full subtractor. The difference expression will be d is equal to x xr y xr z. Then the borrow expression will be x bar z plus x bar y plus y z. Actually here we have 3 input variables x, y, z. Then the difference expression will be x xr y y xr z. So we need 3 input XOR gate to get difference. Then the borrow expression will be x bar z plus x bar y plus y xr z. Now x get inverted to get x bar, then which is multiplied with z, so we need one AND gate. Then x bar is ANDed with y, then y is ANDed with z. Then these 3 ORed together to get borrow. This is the logic diagram for full subtractor. Next let us see multiplexer. What is meant by multiplexer? Multiplexer is a combinational circuit that selects the binary information from one of many inputs and directs it to a single output. Here the selection of the particular input line is controlled by set of selection lines. Now let us see the basic block diagram for multiplexer. This is the basic block diagram for multiplexer. It consists of n number of inputs and m selection lines and one output. Here the selection of the particular input is controlled by the m selected inputs and it transformed to the single output. Next let us see the 2:1 multiplexer. This is the basic block diagram for 2:1 multiplexer. It consists of 2 inputs, 1 selection line and 1 output. Here the selection of this input is controlled by the selection input S and transformed into the single output called Y. Next, let us see the truth table for 2x1 multiplexer. Here S represents selection input, Y represents output. Here the selection input may be 0 or 1. When the selection input is 0, I0 is connected to the output Y. When the selection input is 1, I1 is connected to the output Y. Then from this truth table, let us derive the Boolean expression for Y. Here the out equal to the value of I0 when S is equal to 0. This one represents S bar into I0. Then the output will be equal to the value of I1 when S is equal to 1. This one represents S into I1. Now the final expression will be Y is equal to S bar into I0 plus S into I1. This is the required Boolean expression for the 2x1 multiplexer. Y is equal to S bar into I0 plus S into I1. Now let us see the logic diagram for 2x1 multiplexer. Here we have 1 selection input and 2 data inputs and 1 output. To implement this expression, we need 2 input AND gate, 1 NOT gate and 1 2 input OR gate. S is the selection input. Here inverter is used to take the complement of the selection input. Here the S bar is multiplied with I0. Then S is multiplied with I1. Then these two OR to get Y. Here when S is equal to 0, this one complemented here. Now the output will be 1. This inverter is used to take the complement of the selection input. Here the output will be 1. For this AND gate, one of the input is 1, then the other input is I0. Then the output will be 1 into I0, which is equal to I0. Then for this AND gate, one of its input will be 0, the other input will be I1. Now 0 into I1 is equal to 0. Then these two are OR to get the final output, which is equal to I0. When the selection input is 0, then the output will be equal to the value of I0. Similarly, we can say that when S is equal to 1, the output will be equal to the value of I1. This is the logic diagram for 2x1 multiplexer. Next, let us see 4x1 multiplexer. Next one, 4:1 multiplexer. What is meant by 4:1 multiplexer? It has 4 inputs and 2 selection lines and 1 output. Now let us see the basic block diagram for 4:1 multiplexer. Here I0, I1, I2, I3 are the data inputs. S0 and S1 are the selection inputs and Y is called the output. It consists of 4 inputs, 2 select inputs and 1 output. Next, let us see the truth table for 4x1 multiplexer. Here S0, S1 represents select inputs and Y represents output. Here we have two selection inputs, so there are 4 possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. When the select inputs are 0, 0, then the output will be I0. When the select inputs are 0, 1, then the output will be I1. When the select inputs are 1, 0, then the output will be I2. When the select inputs are 1, 1, then the output will be I3. Here the output is equal to I0 when the select inputs are 0, 0. Then the input I1 is connected to the output when the select inputs are 0, 1. Then the input I1 is connected to the output when the select inputs are 1, 0. Then the input I3 is connected to the output when the select inputs are 1, 1. Then from this truth table, let us derive the Boolean expression for Y. Here the value of Y is equal to I0 when the select inputs are 0, 0. Then this represents S1 bar, S0 bar into I0. Then this one represents S1 bar, S0 I1. Then this one represents S1, S0 bar I2. Then this one represents S1, S0 I3. Then these 4 are summed to get the Boolean expression Y. S1 bar, S0 bar into I0 plus S1 bar, S0 into I1 plus S1, S0 bar into I2 plus S1 into S0 into I3. This is the required expression for 4x1 multiplexer. Then we have to draw the logic diagram for 4x1 multiplexer for this Boolean expression. Here we have two select inputs, S0, S1. This inverter is used to take the complement of S1. Then this one is used to take the complement of S0. Then the Boolean expression Y is equal to S1 bar into S0 bar into I0. To implement this Boolean expression, we need 4 3 input AND gate, 2 inverters and 1 3 input OR gate. Here S0 bar, S1 bar are ANDed with I0 to get S1 bar, S0 bar, I0. Then similarly we can draw S1 bar, this is S1 bar, this is S0 are ANDed with I1. Then S1 into S0 bar are ANDed with I2. Then S1, S0 and I3 are ANDed to get S1, S0, I3. Then these 4 are added together to get the final expression Y. This is the logic diagram for 4x1 multiplexer. Next we are going to see about demultiplexer. What is meant by demultiplexer? Demultiplexer is a combinational circuit that receives the binary information on a single input and directs it to one of many outputs. Here the selection of the particular output line is controlled by set of selection inputs. Now let us see the basic block diagram for demultiplexer. This is the basic block diagram for demultiplexer. It consists of one input, m select inputs and n number of outputs. Here the selection of the particular output line is controlled by set of selection lines. Selection line determines which output going to be selected to receive the input. Next let us see 1 cross 2 demultiplexer. This 1 cross 1 demultiplexer consists of one input and two outputs. Now let us see the basic block diagram for 1:2 demultiplexer. One input, two outputs, D0, D1, one selection input. Now this is the basic block diagram for 1:2 demultiplexer. It consists of one input, one select inputs and two outputs. Here D0 represents output, D1 also represents second output. Now let us see the truth table for 1 cross 2 demultiplexer. We have one select input. Yes, we have two outputs, D0, D1. Here we have single input, select inputs, so this can be either 0 or 1. When S is equal to 0, here the input is connected to D0. When the select input is 1, the input D in is connected to D1. Here the output of D0 will be 0. This is the truth table for 1:2 demultiplexer. From this truth table, let us derive the Boolean expression for D0 and D1. Here D0 is equal to Din when the select input is 0. This one represents S bar into Din. Then here the D1 is equal to Din when the select input S is equal to 1. Then this one represents S into Din. So the corresponding expression D0 is equal to S bar into Din. Then D1 is equal to S into Din. What is meant by 1:4 demultiplexer? It has one input and four outputs, which performs the reverse operation of 4:1 multiplexer. Now let us see the basic block diagram for 1:4 demultiplexer. This is the basic block diagram for 1:4 demultiplexer. It consists of one input, two select input and four outputs, D0, D1, D2, D3. Now let us see the truth table for 1:4 demultiplexer. Here we have 2 select inputs and 4 outputs, D0, D1, D2, D3. Here we have 2 select inputs, so there are 4 possible combinations 0, 0, 0, 1, 1, 0, 1, 1. When the select inputs are 0, 0, the D in is connected to D0. The remaining outputs will be 0. When the select inputs are 0, 1, the data input is connected to D1. The remaining outputs will be 0. When the select inputs are 1, 0, D in is connected to D2. The remaining outputs will be 0. When the select inputs are 1, 1, D in is connected to D3. The remaining outputs will be 0. This is the truth table for 1:4 demultiplexer. Then from this truth table, we can derive the logical expression. Here the output variables are D0, D1, D2, D3. We have to derive the Boolean expression for each output. The first output is D0. Here the input is directly connected to the D0 when the select inputs are 0, 0. Then the corresponding expression will be S1 bar, S0 bar into Din. Similarly, we can write for the remaining outputs D1 is equal to S1 bar, S0 into Din. D2 is equal to S1 into S0 bar into Din. D3 is equal to S1 into S0 into Din. Then by using these Boolean expression, we have to draw the logic diagram for 1:4 demultiplexer. Here we have 2 select inputs, S1, S0. Here these 2 inverters are used to take the complement of the select inputs. We have 4 outputs D0, D1, D2, D3. D0 is equal to S0 bar into S1 bar into Din. Din is the data input. Din is equal to S0 bar into S1 bar into Din. Then D1 is equal to S1 bar into S0 into Din. This one represents S1 bar, this one represents S0, then this one represents Din. Then the D2 is equal to S1 into S0 bar into Din. Then D3 is equal to S1 into S0 into Din. This is the logic diagram for 1:4 demultiplexer. Here the data input is connected to the D0 when the select inputs are S0 and S1 are 0, 0. When S0 is equal to 0, S1 is equal to 0. For this AND gate, the first 2 of its input will be 1, then the third input will be Din, then the final output will be Din. For the remaining 3 AND gates will get disabled. When the select inputs are 0, 1, the second one gets enabled, the remaining 3 are gets disabled. Then the output will be D1 is equal to Din. When the select inputs are 1, 0, then third AND gate will get enabled, the remaining 3 are get disabled due to the first 2 of its input will be high, the third input will be D1. For the rest of the AND gate, any one of the input will be 0. So when the select inputs are 1, 0, this one gets enabled, the remaining 3 gets disabled. For the next combinations 1, 1, the last one gets enabled, the remaining 3 gets disabled, then the final output D3 is equal to Din. Next let us see parity generator and checker. Now we are going to see about parity generator and checker. What is meant by parity? Parity is an extra bit included with the binary message to transmit from one location to another location. Parity bit is used to detect the errors during the transmission of binary message from one location to another location. The parity bit included with the binary message is transmitted and then checked at the receiving end for the errors. Then the parity checker will detect the parity of the received message and compares it with parity of the transmitted message. If they are same, then it understands that there is no error. Otherwise, it understands that the error is present. Now we are going to see about parity generator. What is meant by parity generator? A circuit that generates the parity bit in the transmitter is called parity generator. First, let us see the truth table for parity generator. Now let us consider 2-bit message to be transmitted with the parity bit. Let us take X, Y or the input. P is called parity bit. Actually, the parity bit can be either even parity or parity. For even parity, parity must be generated to increase the total number of ones even. In case of odd parity, parity must be generated to make the total number of ones odd. Here we have 2 inputs, 4 possible combinations 0, 0, 0, 1, 1, 0, 1, 1. Here the first combination is 0, 0. First let us consider even parity. 0, 0, which consists of even number of ones. This one represents no one. Then which is an even number. 0 is even number. Then this one produces 0. The second combination is 0, 1. This consists of odd number of ones. Then this one produces 1 to make the total number of ones even. Now the total number of 1 is 2. This is an even number. The third combination is 1, 0. Now this consists of odd number of ones. Then the parity bit generates 1. Then the next combination is 1, 1. This consists of even number of 1. Now this one generates 0. Then from this truth table, let us derive the Boolean expression for parity bit. Here we have 2 input variables, so we need 2 variable K map. X, Y are the inputs 0, 1, 0, 1. Here the parity bit will be 1 for the combination 0, 1, 1, 0. So the expression for the parity will be, this one represents X bar Y, this one represents X Y bar. X bar Y plus X Y bar. Now this is expressed in sum of product form, then this can be written as X XOR Y. This is the Boolean expression for parity. Then using this Boolean expression, we have to draw the logic diagram for parity generator. Here we have 2 inputs X and Y. Then the expression for parity generation is X XOR Y. So we need one XOR gate. This is the logic diagram for parity generator, which is P is called as parity bit, which is equal to X XOR Y. When both the inputs are 0, then the output will be 0. When both the inputs are 1, then the output will be 0. When any one of the input is 1, this one produces 1. Now we are going to see about magnitude comparator. What is meant by magnitude comparator? Magnitude comparator is a combinational circuit that compares the magnitude of two numbers and determine their relative magnitudes, namely A less than B, A equal to B and A greater than B. Now let us see the basic block diagram for magnitude comparator. This is the basic block diagram for magnitude comparator. It consists of two binary numbers and we have three outputs, A less than B, A equal to B, A greater than B. First let us see two 1-bit magnitude comparator. First let us see the truth table for 1-bit magnitude comparator. Here we have two inputs, A and B. Here A and B are the two 1-bit number. We have three outputs, A less than B, A equal to B and A greater than B. Here we have two input variables, so there are four possible combinations 0, 0, 0, 1, 1, 0, 1, 1. Here the first combination is 0, 0. Now we have to compare A with B. Now 0 is equal to 0. So the output will be 1 for A equal to B. For the remaining outputs will be 0. Here the second combination is 0, 1. Here the 0 is less than 1. So this one will be 1, then the remaining two outputs will be 0. Then the third combination is 1, 0. Now 1 is greater than 0. So A is greater than B. Then the remaining outputs will be 0. Then the fourth input is 1, 1. 1 is equal to 1. So A is equal to B. Then the remaining outputs will be 0. This is the truth table for 1-bit magnitude comparator. From this truth table, let us derive the Boolean expression for A less than B, A equal to B and A greater than B. First one for A less than B. Here we have two input variables, so we need two variable K map. A may be 0 or 1, B may be 0 or 1. Here A less than B will be 1 for the input combination 0, 1. So the corresponding expression will be A bar B. Second one, the Boolean expression for A equal to B. A and B are the input variables. Here the output A equal to B will be 1 for the input combinations 0, 0, 1, 1. This one represents 0, 0, this square represents 1, 1. So the expression will be, this one represents A bar, B bar. Then this one represents AB. Then this is looks like XOR Boolean expression which is equal to A XOR B. Next, let us see the Boolean expression for A greater than B. We need two variable K map. Here the output A greater than B will be 1 for the combination 1 0. This square represents 1 0, then the corresponding Boolean expression will be this 1 represents A B bar. Then we have to draw the logic diagram for A less than B, A equal to B, A greater than B. Here we have two input variables A, B. Then these two inverters are used to take the complement of the input. The first output will be A less than B. A less than B is equal to A bar B. This one represents A bar, this one represents B. A bar is ANDed with B to get A less than B. The next Boolean expression will be A equal to B, which is equal to A XOR B. To implement this output, A is XORed with B. Here A is XORed with B to get the Boolean expression A equal to B. The next output will be A greater than B. A greater than B is equal to A B bar. This one represents A, this one represents B bar. A bar, A ANDed with B bar to get A greater than B. This is the basic logic diagram for 1-bit magnitude comparator. Now we are going to see about summary of this lecture. Actually in this lecture we have discussed about combinational circuits, adders, subtractors, multiplexers, demultiplexers, parity generator and checkers, and magnitude comparators. Then what is meant by combinational circuit? Combinational circuit is a logic circuit in which the output depends only on the present combination of inputs. Then what is meant by adder? Adder is a combinational circuit that performs the addition of two binary digits. Then adder classified into two types. The first one is half adder, then the second one is full adder. The next one is subtractor. Subtractor is also combinational circuit that performs the subtraction of two binary numbers. Then the subtractor classified into two types. The first one is half subtractor, the second one is full subtractor. Next one, multiplexer. Multiplexer is also combinational circuit that selects the binary information from one of many inputs and directs it to single output. The next one is demultiplexer. Demultiplexer is also combinational circuit that performs the reverse operation of multiplexer. The last topic is comparator. Comparator is a combinational circuit that compares the magnitude of two numbers and it determines their relative magnitudes, namely A less than B, A equal to B and A greater than B.